So we want to pick up from our chemistry section, which we began last time. I think we stopped here, right? Is that right? At the idea of atomic numbers. So let's go back and do a quick review because it's a lot of unfamiliar terms. It'll be useful to see these terms again because we're going to continue to go back to them going forward. When we were talking about chemistry last time, we were talking about atoms, molecules, elements, and then the subatomic particles that are coming together to make up the atom. These guys down here. And we were kind of using an analogy of the alphabet. We said an atom is like a single letter of the alphabet that can be combined with other atoms to make a molecule. For example, a water molecule is what we're seeing here. So the molecule is kind of like a word made from separate letters. The same way the molecule is made from separate atoms. We have different types of atoms that can exist. So, for example, when we had our water molecule, we had 2 hydrogens and an oxygen. And there's, I don't know, like about 200 different types of atoms that can exist, and we call each of those things, each of those flavors of atom that can exist in the world, we call that an element. And here we have a list of all the elements. Similarly, we know there's 26 letters in the alphabet, right? So we know there's 26 letters in the alphabet. We could write all 26 of those letters here in a list of the alphabet. So that's kind of like what our periodic table is, a list of the elements. That's kind of like a description of the alphabet that we have down here. And then we said that each atom, could be broken down into smaller parts. It's just that the atom makes a little less sense once you start breaking it down like that. It stops being what it is. It stops being an atom of a particular element once you start breaking it down. The same way you could break down a letter into its individual pieces. You could break down a letter into the specific lines that make it up. But it would stop being the letter A if you took a piece of it away. The same way this atom, this carbon atom, would stop being a carbon atom if you took certain of its subatomic particles away. So the subatomic particles are really what are defining an atom as a particular type of atom. This is what's determining that our helium atom is a helium atom and our carbon atom is a carbon atom. It's all about the number of subatomic particles that it has. And we can give our subatomic particles names. So we said in the center of the atom we have protons and neutrons, forming what's called the nucleus of the atom, not to be confused later with the nucleus of a cell that we'll see. This is the nucleus of the atom, these larger particles in the center. And then we have our smaller particles existing outside of that larger center. These are our electrons. They're very, very small, smaller than you can appreciate from this diagram. And they're existing around the nucleus in these sort of what look like circles on this diagram, but are really more like clouds around the center of that atom. And there are these electric charges associated with these things. So our protons in the center are always positively charged. The electrons are always negatively charged. And then our neutrons are always going to be neutral. They're not going to have an electric charge associated with them. So we call them neutral. So again, the thing that makes an atom of one element different from an atom of another element is its number of subatomic particles. So if we're looking at carbon here and we're comparing it to nitrogen, our carbon atom has 6 protons, 6 neutrons, and 6 electrons. That's what makes it carbon. In particular, it's the protons here. This is what we see on the next slide. The 6 protons in particular is what makes it carbon. And that's in comparison to nitrogen. So our example of our nitrogen atom up here has 7 protons, 7 neutrons, and 7 electrons. And specifically the fact that it has 7 protons is what makes it a nitrogen atom. So that brings us to where we left off with this idea that the number of protons determines what element a particular atom is. And we call that number, the number of protons that an atom has, we call that the atomic number. And so if we looked at the periodic table, if we looked at that list of possible elements in the physical world, we could see that each one of those elements that were listed there had a number in the upper left corner, and that number is the atomic number. That number tells us that any atom with 6 protons is a carbon atom, that any atom with 7 protons is a nitrogen atom, because we know the atomic number for each of these elements. At the bottom of our periodic table entry, we see atomic mass. and that's the number that's listed here. Oh, is that a question?
Yeah.
Yeah.
I don't know if I missed it. Will there be any significance addressing quirks?
Quarks?
Yeah.
No.
No.
No, we're not getting into that. This is like very, very basic overview chemistry, so we can understand the biology. So we won't be getting into that sort of stuff. Hold on. So atoms are will typically have a similar number of protons and neutrons, and that's what we saw here. Right, 6 protons, 6 neutrons in our carbon, 7 protons, 7 neutrons in our nitrogen. So typically it's around the same number, although sometimes you have an atom of carbon with 6 protons and 7 neutrons. So there's a little bit of variation in the number of neutrons a particular atom can have. And we can define this term atomic mass as the number of protons plus the number of neutrons. So you might say that this particular carbon that we saw back here, what would its atomic mass be, this carbon here, if it's number of protons plus number of neutrons? Well, yeah, simple arithmetic, just adding up these two numbers together. Or nitrogen, what would its atomic mass be? 14. What these numbers in our periodic table for the atomic mass of each of these things are actually showing us is the average atomic mass of carbon atoms that exist in the universe. So we said some of them are going to have 6 neutrons, some of them are going to have 7 neutrons, and so we'll have an atomic mass of 13 instead. Most of the carbon atoms are just going to be 6 and 6. Some, a fairly small proportion of the carbon atoms are going to be 6 and 7. And if you average all those carbon atoms together, the mass of all those carbon atoms, you get something like 12.011. And so that's how we get this sort of uneven number for the atomic mass of carbon in general in the universe, because it is this average. And our periodic table, if we look at it closely, is arranged from left to right in order of atomic number. So starting with 1 all the way up there, we have hydrogen, we have helium, so reading from left to right. Hydrogen, helium has an atomic number of 2, lithium has an atomic number of 3, beryllium has an atomic number of 4, and we can keep going, we can keep reading right to left like that. So when we're talking about biology, there's actually a fairly small set of elements that we'll really concern ourselves with. And for the most part, they have fairly small atomic numbers, and that's kind of going to limit the amount of chemistry that we have to cover before we can actually jump into the biology. So that's a little bit of good news. And you'll see as we go through this lecture, I'm focusing on the ones that are important for biology. So we've already talked about carbon and nitrogen. Those are going to be some of the elements that are particularly important for biology. Oxygen, hydrogen, these things are we're going to see them over and over again when we talk about biology. So an atom often has the same number of neutrons as it does protons, and it should also have the same number of electrons that it does protons as well. And with equal numbers of protons and electrons, all of the positive charges on the protons and all the negative charges carried on those electrons cancel each other out. So if you're ever trying to figure out the overall charge of an atom, you kind of add up all the protons, and you give that a positive number. So we have 6 protons, so that would be like positive number 6 here. And if we have 6 electrons, that's like a negative number that we're subtracting from it. So if you have positive 6 minus 6, what do you end up with? 0. Yeah. So overall, our atom doesn't have a charge because those protons and those electrons are canceling each other out. Another way to write this, I mean, it depends on what makes sense to you. It's kind of all the same. You could also write 6 plus negative 6, representing the positive 6 from the protons, negative 6 from the electrons. Or you could just say 6 minus 6. Whatever makes sense to you. And the number of electrons is of particular importance. This is actually what we'll want to pay attention to with all these atoms, is because that's what determines how one atom interacts with other atoms, and in fact how an atom interacts with other atoms to form the molecules that we were seeing. That hydrogen molecule that we were seeing formed because of how the electrons on hydrogen, the water molecule we were seeing formed because of how the electrons on hydrogen and the electrons on oxygen interacted with one another to form that molecule. So to understand this, we have to go a little bit deeper into the chemistry here. Maybe you already noticed that when we had our 6 electrons around our carbon atom, we drew them in a particular way. We had drawn these 2 circles outside of the nucleus, and there were 2 electrons in that inner circle. There were 4 electrons in that outer circle, and that meant something. That wasn't just like a cute way we decided to draw it. That had actual meaning. We just hadn't talked about that yet. So now let's talk about those circles. Those circles are representing shells that exist around the nucleus. So these are different levels that the electrons can exist at. The electrons can exist in a shell that's very close to the nucleus, or they can exist in one of these other shells that are a little bit farther from the nucleus. Each shell can only hold a certain number of electrons. This is a really weird, I don't know, chemistry, this stuff is all like a weird sort of abstract concept, but that's how this works. Each one of these shells can only hold a certain number of electrons. So this inner shell can only hold 2 electrons. You can't have more than 2 electrons in this shell. And that's why our carbon atom, having filled up this inner shell with 2 electrons, put its remaining 4 electrons in the second shell. The second shell can hold up to 8 electrons. And then if the atom fills up the second shell with electrons, then electrons start being added to the third shell. The third shell can also hold 8 electrons, and then after that point, the atom would start adding the electrons to a 4th shell. And so on, but luckily for us, like I said, we're dealing with things with relatively small atomic numbers, so we don't really have to deal with any shells besides the first, the second, and occasionally the third. We don't really have to think about anything else. So whatever the outermost shell is, so in our carbon example where we had 2 electrons here, 4 electrons in our second shell, we didn't really have anything in the third shell. There weren't enough electrons that the atom needed to go to that third shell. In that example, we would call that second shell the valence shell. That's the outermost shell that an atom is filling with electrons. If an atom doesn't have any electrons in that third shell basically doesn't exist for that atom. But that second shell, in our example of carbon, that was our valence shell, the outermost shell. Let's go back to carbon just so we make sure we see that, right? When we drew out carbon, this is how we drew it, with just 2 shells, 2 electrons in that inner shell, 4, the remaining 4 in that second shell. So in this case, this is the valence shell for carbon. What we're looking at here, that third shell, is our valence shell, because this atom has electrons in this third shell. And for both, what are we looking at here? I always forget. It's either chlorine or sodium. Sorry, I have to do a little bit of math to remember. This would be chlorine. So chlorine has this third shell as its valence shell, and it's not happy with that. All atoms want to have valence shells that are completely filled with electrons. So chlorine is going to try to do something to completely fill this third valence shell with electrons. It's going to basically try to fill in this electron that's missing from this valence shell that would get it to 8 electrons in this valence shell. Similarly, carbon, which we saw back here, also has an unfilled valence shell. It has 4 electrons in the second shell, but the second shell can hold up to 8 electrons. So carbon is also going to want to fill its valence shell, in this case its second shell, with some more electrons to fill up all those spots. And that's really what's driving how atoms are interacting with each other and how they're forming bonds with each other, in particular covalent bonds. So in an atom's quest to fill its valence shell, there's 2 main ways that we'll think about that an atom can actually accomplish this. One way that an atom can accomplish this is by sort of arranging a sharing agreement with another atom. The 2 atoms will agree to sort of pool some of their electrons together and share some of their electrons in order to each have filled valence shells. So when that happens, that's called a covalent bond, and that's what we'll discuss first. And then another way an atom can achieve a filled valence shell is it can just get rid of an electron, or it can pick up an electron from some other atom that was trying to get rid of an electron. So that's another way that certain atoms are going to achieve a filled valence shell, just by gaining or losing an electron. And when that happens, they'll become something different. They'll become ions. So we'll talk about that as well. But starting with covalent bonds, And these are what are going to form most of the molecules we'll see. Our water molecule was formed from covalent bonds. We can look at this particular example as a nice starting point. So again, the idea here is when two or more atoms are deciding to pool their resources together, they become stuck to one another. And that's what we see here. So let's start with our individual atoms and how they began. We have two hydrogen atoms here. Hydrogen, if we looked at that periodic table, hydrogen's atomic number was 1. So how many electrons did it start off with? 1, yep, and 1 proton and 1 electron. And it's not happy with that, right? So how many electrons does it actually want? 2, yeah, because that inner shell can hold up to 2 electrons. So that's what hydrogen is trying to achieve. So the way it achieves that is it pairs up with another hydrogen atom. These two hydrogen atoms come together, and they create a little space where both their electrons are shared. So this hydrogen atom is donating its 1 electron, this hydrogen atom is donating its electron. They created the space where the electrons are shared, and now they're stuck together. So they're happy because their valence shells are filled, but they can't go anywhere. They're stuck to one another, they're bonded to one another. And when two or more atoms are bonded to one another in this way, we call them a molecule. We can represent this a few different ways. So this is sort of the most complicated way we could represent this with these drawings where we're actually drawing out the electrons physically. We don't really ever need to do that in this class in biology. Something that will be a little bit more useful for us is understanding this way of writing out this hydrogen molecule. So, and this I should say is hydrogen gas. So we have these two hydrogen atoms coming together to form this molecule of what we would encounter in the world as hydrogen gas. So this is the way we can represent hydrogen gas. This is the way we can represent this molecule that's been created. It's just by writing the abbreviation for hydrogen. So there's hydrogen and hydrogen. We have these two hydrogen atoms that come together. And we have a dash in between, and that represents the covalent bond that's connecting them. So that's what we would call a chemical structure. It's sort of a drawing of the atoms that are making up this molecule with these little lines that show the covalent bonds that connect them. Yeah, question?
If they don't bond with a different chemical, do they just become a larger atom, or do they become something else?
I think we'll see that in a slide or two. We'll see a case where it's, yeah, so you can have cases where it's two hydrogen atoms. You can also have two hydrogens and an oxygen to form water. So there are like technically different names for them that we don't really have to know, but it's very similar in principle. That's what I'd say. So we have our bond represented by this dash. We have our two hydrogens represented by the chemical abbreviation for hydrogen here, and that's what's called a chemical structure when our molecule is represented that way. And then finally, an even simpler way to represent this molecule that's been created as we're trying to talk about it and trying to communicate about it is just by representing it as a chemical formula. This is kind of just a list of atoms that make up a molecule without any representation that's showing exactly where those covalent bonds are. We're just sort of listing out all the things that went into that molecule. Question?
Now, if it's merging with something, does it turn into a different type of element, or is it becoming bigger? And in theory, if it becomes big enough, would it be able to destabilize and make something else?
So they're actually much more stable when they come together like this. But I think the question that you're saying about, like, do they become something different? In some sense, no. So they can break apart again and then combine with other atoms. So this hydrogen gas in a chemical reaction could break apart back into hydrogen atoms, and those hydrogen atoms could combine with other atoms to create some new form of molecule. So these hydrogen atoms are still hydrogen atoms that can be broken apart. But this molecule is going to have very different properties than the properties of the atoms individually. So I don't actually know if a hydrogen atom exists in the universe, what it's doing, what form it takes, and I don't know if it exists as a solid or a gas. But I do know that when these two things come together, and that's the much more common thing, is to see something like this, where these two things have come together and formed this more stable molecule that exists as a gas in the universe. So yeah, this molecule that's formed from these different elements is going to have very different properties than any of these atoms on their own. Does that answer your question? Okay. Yeah.
Chemical structure and chemical formula, are they the same thing but just written differently?
Yeah, exactly. So Moving on to the next slide might help clarify some of these concepts. So this is a more complicated molecule. Here we have atoms of different elements that are coming together, not just two hydrogen atoms, although we do have two hydrogen atoms that are involved here in this sort of sharing of electrons. But we also have two nitrogen atoms, which are also trying to fill their valence shells. And if you want to, you can take some time out of class to really try to figure out how this sharing arrangement is working. All the electrons are color-coded with which atom they started from, so you can see that these two nitrogens have each donated 2 electrons to this sort of shared resource of 4 electrons between them. And then this nitrogen also donating an electron to this sort of shared resource with this hydrogen atom. But it's perfectly arranged in a way where all of these individual atoms that are now making up this molecule are happy. Each one of these now has the filled valence shell that it was trying to get through these sharing arrangements with other atoms, forming these bonds. So this bond between the nitrogen and the hydrogen here, this nitrogen and this hydrogen, that's a single bond, so we're representing it on our chemical structure as just that single line. And then here, when we have not just 2 electrons shared between them, but 4 electrons shared between them, that's a double bond. So we're representing it with 2 lines here. And we can simplify this again into a chemical formula. So we could call it H2N2, representing the 2 hydrogen atoms and the 2 nitrogen atoms that went into this molecule. And you can imagine the scenario. So it's just sometimes useful for us as biologists to look at these things different ways. So sometimes we'll just want to write the chemical formula. That's probably more often for us in biology. We don't necessarily care about the chemical structure in a lot of detail. We might be interested in it a little bit, but usually it's good enough for us to just know the chemical formula of what we're dealing with. But you can imagine a situation, even in biology, where the chemical structure becomes important or interesting. And you can also imagine a situation where the chemical formula could potentially produce multiple different chemical structures. So actually, when we talk about glucose, which is basically a molecule of sugar, glucose has a particular chemical formula, and it actually has a few different ways that all those atoms can be arranged to form that glucose molecule. It can sort of exist as a straight line, or it can exist as a ring. The chemical structure can look like a ring, like a hexagon. So we will actually see that, I think, much later in this lecture. Maybe we'll get to it today. But we'll see the chemical structure of something like glucose. And we'll see that it'll look more complicated than this. And we may or may not see that the chemical formula for glucose can be arranged in different ways. I forget if I actually showed you the 2 different forms of glucose. I know I showed you the hexagon form of glucose. I don't remember if I showed you the other one. But it can take on those 2 different forms. Any questions? So carbon is a really special molecule when we're talking about covalent bonds and when we're talking about the chemistry of life. So if we just go back here to look at our carbon atom again, one of the things that's really, in some ways, useful about carbon is that it's trying to get this shell with 8 electrons, and it has 4 electrons, and that kind of leaves it 4 open spots to bond with some other type of atom to form a molecule. This is different than hydrogen, which, again, like thinking about the idea of open spots might require a little reflection when you guys are at home, if that's something you really want to understand, this idea of like open spots and what atoms can really bond with other atoms to form a molecule and how many spots they have open. But I'll tell you that if we think about hydrogen, and this should make a little bit of sense, hydrogen really has only 1 open spot for another electron to come in before it achieves that filled valence shell. When we were talking about nitrogen, it had 3 open spots. So it had 5 electrons in the shell that wanted 8 electrons total. So it had 3 open spots for electrons to come in from other atoms to form those bonds so that this nitrogen could get its filled valence shell. But carbon has 4 open spots, so it can form up to 4 bonds with something else. And it needs to form up 4 bonds with something else to get that filled valence shell. And that gives it this ability to make these really complicated chemical structures, much larger and more complex than anything you could get with just oxygen and hydrogen and nitrogen alone. Again, you can sort of like sketch this stuff out at home if you think this is really cool and interesting, and you'll find a limit to the atoms that you can build with hydrogen and oxygen and nitrogen But with carbon, once you get carbon in the mix, there's really no limit, because carbon does have these 4 spots that it can use to bond with other things. And so you get these very large, complicated things like this, which is a triglyceride molecule. You can get things that are even larger and more complicated than this. So for example, DNA maybe starts around, each base in DNA is maybe around this size, but then they get strung together into a molecule that's actually millions of bases long. So if you sort of took this part of this, but multiplied it by 1,000,000, that's how long a DNA molecule would be, but it's a single molecule. And the reason it's able to build up like that is because it's mostly made of carbon that has these 4 spots that can be filled in by covalent bonds. And so that's why carbon is so important for life. It's creating these huge complex molecules that are important for our very complex bodies to exist in the world as matter, right? Our bodies are much more complicated than the air that we're breathing, which is oxygen gas and nitrogen gas. Our bodies have all these like really hard tasks to do. And so it's these really complicated organic molecules that are being formed mostly of carbon that are allowing our bodies to do all these really complicated tasks. So we have this word organic that we're applying here. So it's fairly important to distinguish from our idea of like organic food. If I've told you that basically everything living is made up of organic molecules, that means all of the food, everything living and everything formerly living is made up mostly of organic molecules, and that means all the food you eat is made up of organic molecules, hopefully. If you want to be able to digest it, all of the food should be made up of organic molecules. So that's completely different from our idea of like organic farming. That's just like completely different use of the word organic. When we're talking about chemistry, any of these molecules that are going into building something living, any of these molecules that have this basis of carbon are organic molecules, and it has nothing to do with whether something was organically farmed or not. And then we have this word macromolecules, too, which I haven't quite defined. So molecules we've defined. We've been talking about molecules for the past couple slides. Macro is a prefix that just means big. So a macromolecule is just a big molecule formed with lots of carbon as well as some other stuff. So we're going to be doing a lot of that sort of thing in this class in human biology, where we're breaking down words into their prefixes and roots and suffixes. Understanding the prefixes, the roots, the suffixes, all of this stuff is going to help us understand the language of anatomy and physiology a lot better, because it is in many ways like learning a language. So breaking it down like that would be very helpful. So you probably, if you haven't already, you should probably jot that down in your notes, that macro means large, and so a macromolecule is a very large molecule. Okay, so that's our discussion of covalent bonds and how covalent bonds have come together to bring atoms together to form a molecule. Now let's get to a completely different way an atom can achieve a filled valence shell, and that's by just getting rid of an electron or just picking up an electron from something else that was trying to get rid of it. So we have 2 examples that we can look at here. We have the chlorine atom that we saw earlier. You'll recall, if you look at all these blue electrons here, those were all in our chlorine atom that we saw earlier. But it was missing that one up there, right? It had this almost filled valence shell, but its valence shell wasn't quite filled yet. This is showing us a chlorine atom that has picked up an electron from somewhere else. That's what that green electron is. It wasn't there to begin with, but it's this chlorine atom has picked it up. And now actually this chlorine atom, now that it's picked up another electron from somewhere else, we actually wouldn't call it an atom anymore, we would call it an ion. The other thing that you'll notice has changed about this chlorine atom is its electric charge has changed. So before we said if our chlorine atom had 17 protons and 17 electrons, it had a neutral charge. So let's try to figure out what the charge of our chlorine atom is now. So try to do that math, keeping in mind that each proton contributed 1 positive charge and each electron contributed 1 negative charge. Just do that little bit of arithmetic to figure out what the charge of this chlorine ion is now. You can write it down in your notes. Sketch out the formula, even at, like, right, because this is math that you can do in your head, but sketch out the formula just so you know. Okay, so what did we write down for our equation and what answer did we come up with? Who wants to raise their hand and volunteer? Yeah?
-1.
Yeah, so our answer was -1, and hopefully we got there somehow by looking at these 17 protons with positive charges, and then, yeah, we can do it the simple way, subtracting our 18 electrons with negative charges. So 17 minus 18 is going to be -1. So that's our new charge for our chlorine ion that's formed. Then we have sodium down here. So here with sodium we have 11 protons. So when sodium started off, it had 11 protons and it had 1 electron in that outermost valence shell. And now it's gotten rid of that electron. Maybe it donated it to chlorine. Now that it's gotten rid of that electron, it's happy because now its valence shell is its second shell, and its second shell is full. So what's the charge of our sodium ion? Who can do the math and give me an answer for this?
Positive 11 minus 10, so it's 1.
Yeah, exactly. So we have 11 protons with those positive charges, just 10 electrons with that negative charge, so that gives us an overall charge of +1. So we have some of these ions with negative charges, like chlorine up here. We have some of these positive charges, like sodium down here. And in biology, we don't really see this formation of these ions. So these two ions can start to exist in the world because of a really violent reaction that occurs between a sodium atom and a chlorine atom that produces these ions. It, like, I don't know, it burns. Like when this reaction occurs, it's very violent, it lets off a lot of heat. It's not something that actually happens in our bodies. So it's not something that our bodies really want to or are equipped to deal with. So in biology, we don't really deal with the formation of these ions too much, and that's why I haven't shown you a lot about the formation of these ions. But a lot of these ions already exist in the world. So for example, sodium chloride is table salt. Sodium chloride already has these ions, these sodium ions, and these chlorine ions together forming sodium chloride, the substance. So we see a lot of ions in biology. We don't have to worry too much about how they got there, but we'll see these things over and over again. Question?
So if it's an ion, what does it mean for its properties? Is it just a new component, or is it just energy?
Yeah, so this positive charge and this negative charge, they mean a lot for how these things are going to behave in the world. So the most important thing about the positive charge and the negative charge, should just jump right into the next slide, is that they're going to be attracted to one another. So whereas our original sodium atom and chlorine atom wouldn't want to stick together, our sodium ion with its positive charge and our chlorine ion with its negative charge, they are going to want to stick together because those opposite charges are always attracted to one another. If you've ever heard the term opposites attract, this is really a case where this is true in chemistry. So sodium and chlorine, these two ions with these two charges, are going to want to stick together. Those opposite charges are going to want to bring these things together. And that's creating what's called an ionic bond. So it's holding together ions with these opposite charges. So this is a bond. It's different than our covalent bond. In our covalent bond, these two things would have actually been sharing electrons. And it would have been really, really hard to pull them apart. This is a little different. It's a little easier to pull these positive charges away from these negative charges. They're stuck together just a little less tightly than they were with our covalent bond. Did I already say that sodium chloride is table salt? Mm-hmm. Okay, good. Because that's really important. Like, we'll see sodium chloride, like we'll see these things in the body a lot. And I think it's useful to think about how they got there. So actually, like, sodium and chloride are both really important for the nervous system, how the nervous system is functioning, really important for how the muscles are functioning. Like, these are like really necessary things. We do want to think about how they got there, and in the case of these two particular ions, they're coming into our body through table salt. So that's kind of a lens. As we get further and further into the chemistry lecture, we'll start to pull in more facts. I feel like they're a little bit more related to biology, in some ways a little bit related to nutrition, like that one. So we're starting to build up towards an understanding of biology and not just chemistry. And this is kind of the beginning. Okay, so once atoms are bonded together, and this is in particular talking about a covalent bond. Once atoms are bonded together in a covalent bond and they're sharing their electrons are going to exist in these sort of shared clouds. Previously they were in their separate clouds, their separate shells. Now that they're together, they're existing in these shared clouds around the nuclei of these two atoms that came together to form this molecule. So here we have a case where you just have two carbons coming together, and their electrons are existing in this cloud around these two carbons. And they're kind of equally distributed. If you look at the shape that these clouds are drawn in, it's symmetrical, right? You could draw a line down here and there would be an equal amount of cloud on one side as there is on the other side. And that's because the electrons are going to be evenly shared between these two. The electrons aren't just sitting in one spot. That's the other weird thing about the electrons, is they're floating, they're moving all the time. So this is just sort of showing us where they tend to hang out. This is a different scenario. So here we have our oxygen nucleus over here, bless you, and our hydrogen nucleus over here. And the oxygen nucleus is actually going to pull the electrons towards it a little bit more than the hydrogen nucleus is. So you're actually going to get these kind of uneven clouds that these electrons are floating in. And that's going to create these slight positive and slight negative charges across this molecule. This molecule overall, its charge is neutral, but if we sort of look at it in detail, we see there are places that have a slight negative charge and places that have a slight positive charge. So here again, so we give this a name. So we would say this is considered polar if we see this asymmetry in the charges. This is a polar molecule, whereas this would be a nonpolar molecule. And the reason this is important is because it's still true that the opposite charges are going to be attracted to one another. Again, these are slight positive and slight negative charges, so they're going to be less attracted to each other than those ions were, but they are going to be weakly attracted to each other. And that's when that occurs, when these molecules have this very weak attraction to each other. That's called a hydrogen bond. And that's actually what we're seeing here. So we're seeing this here with water as an example, where we have the oxygen atom that's forming water pulling electrons toward it just a little bit more tightly than our hydrogen atoms, creating this weak negative charge on this end and these weak positive charges on this end. And these weak negative and weak positive charges on all these water molecules that are filling some sort of space are a little bit attracted to each other. And that's actually what gives water its cohesiveness, its tendency to stick to itself. So if you put a drop of water on a surface, it tends to bead up. It doesn't tend to just spread out completely over a flat table. It doesn't immediately evaporate. It's sticking to itself a little bit, and that cohesiveness is because of these hydrogen bonds that are forming between these different water molecules. So I kind of have some I think it's kind of confusing to call hydrogen bonds bonds. Like really when we're talking about two things being bonded together, we're usually talking about a covalent bond. Sometimes we're talking about an ionic bond. This is a way that different molecules can be kind of attracted to each other. So when we're talking about biology, I would think about this as an attraction more than it is a bond, because it's very easy to pull these things apart again once they've formed. But it is something that are helping certain molecules stay together. We see it with water. We actually see it with DNA. We'll see hydrogen bonds come back with DNA and maybe a base pairing. If that's something you've heard about before. So they are relevant in biology, but it's more of an attraction than a bonding per se. So for listing these chemical bonds from strongest to weakest, which one did we say? Well, everyone, we've had this discussion and we've gone straight through it. So write down in your notes what the chemical bonds are from strongest to weakest, and then we'll check our answers together. Okay, so what did we say was our strongest bond?
Covalent.
That's our covalent. Our second strongest bond, ionic, where we had those two ions coming together with those positive and negative charges. And then our weakest bond, not really a bond at all. I think this is what everyone was saying, hydrogen. Or sometimes called a polar bond. It's called a hydrogen bond because hydrogen is often involved in like the chemical structures that tend to want to form hydrogen bonds. It's not that every hydrogen is going to try to form a hydrogen bond, but if we looked at water, we could see that water had hydrogens and it tended to form these hydrogen bonds. Just a side note on the names of things. Sometimes the names that we'll see in this class make a lot of sense. Sometimes they make no sense. Sometimes they make some intermediate amount of sense. I think it's helpful to know where the names come from, and to acknowledge how much sense it actually makes when things are named a certain way. This is like a medium amount of sense calling these things hydrogen bonds. Anyway, this is our order of strength of covalent bonds. Covalent are the strongest. That's where we found the sharing of electrons. Very hard to pull those atoms apart again. Ionic, that was a little bit weaker between the ions with positive charges and negative charges. And then we have just these slight positive and negative charges across molecules, giving them some weak attraction to each other with our hydrogen or polar bonds. So most of the molecules we discuss in the class, all these big organic molecules that are doing all this important work in the body, most of those are formed by very strong covalent bonds. Occasionally we'll see ions, like sodium and chloride, coming together to form these ionic bonds. And we'll see the important jobs that ions do in the body. And then we have a few rare circumstances where it's useful for us to think about this weakest sort of attraction with our hydrogen or polar bonds, bringing molecules together to give them a sort of stickiness to one another. And then a final subject that we want to cover in our basic chemistry review is the idea of chemical reactions. So this is just any time one chemical or set of chemicals is converted to a different sort of chemical. So this is usually involving the breaking of bonds and the reforming of bonds. And this is all going to be, well, we talk a lot about how energy is involved in these chemical reactions too. So a lot of them are going to require a little bit of energy to get started, and whether or not these chemical reactions actually happen or not has to do a lot with the energy of those different chemicals as well. So I don't want to get too far into that because that can be kind of confusing. Let's just start with the basics. The idea is that we have different types of chemical reactions that can occur. There are some reactions where you're taking maybe two separate molecules. This isn't really representing atoms or anything like that. This is just sort of a generic notation for generic molecules. So we're just calling one molecule A and another molecule B. And maybe those two molecules come together and they form something new, something bigger, which we'll call AB. That's a chemical reaction. You're forming new bonds between these previously separate molecules. So that's what we would call a synthesis reaction. You get into the opposite thing, which is a decomposition reaction. So you have some sort of molecule and it's breaking apart into two pieces. So maybe our AB falls back apart into just A and B. And then you can have an exchange reaction where you have, let's have two chemicals. One we'll call AB, so we have a bunch of molecules of AB. We'll call the next one CD. So we can have a bunch of molecules of that. And they can react with each other in a way where they're kind of swapping components. Again, all these bonds are breaking, forming again, and maybe what you end up with after this chemical reaction occurs is AC and BD, where AB chemical has kind of swapped some piece of itself with the CD chemical. So that's what we would call an exchange reaction. Whenever we're talking about a chemical reaction, we have reactants, or whatever is going into the reaction. So the way these are notated, all of our reactants are over here. And then the things that come out of the reaction are the products. So the products are what we're seeing on the other side of our arrows here. Just two terms that we'll see a lot. Probably more useful to memorize these than it is to know synthesis, decomposition, and exchange. This idea of reactants and products is something we'll see more often. And every chemical reaction does either release or absorb some energy. And that's something we'll touch on too. This is really important when we talk about metabolism, which we'll do very, very shortly. And we'll talk about types of chemical reactions that are going to release energy and types of chemical reactions that are going to absorb energy. And that's going to be important for how the body is using these chemical reactions to fuel itself, to make what it needs. That idea of absorbing and releasing energy is something we're going to come back to. So that covers our basic chemistry part of the lecture. And again, if that seemed like a lot, it's because we covered like the first third of a chemistry course in like 2 days. So what's on your study guide is actually a pretty simple overview if you've looked at that. Not a lot about electrons, not a lot about the details of covalent bonds, but more about understanding in general what a covalent bond is and what a molecule is and what an atom is. That's what I want everyone to actually take away from this stuff. So hopefully we understand our definitions of matter in chemistry, our definitions of atom and molecule being very important, especially molecule. Whenever we talk about molecules in this class, you want to kind of understand what we're talking about. We understand our 3 types of covalent bonds that can connect atoms or connect molecules. We understood our definition of an ion, which has that positive or negative charge. What makes it different from an atom, that positive or negative charge. And then we understood chemical reactions, the conversion of one set of molecules to another set of molecules. So I think this is a good spot to take, say, a 7-minute break. 10 minutes felt a little long last time, so let's take 7 minutes. We'll regroup at 4:42. Question?
Yeah,
Before we break. Is this a before we break question, or is it?
I can just ask you, or we can do before break. I don't really care.
Go for it.
I was just wondering, so whenever you were going over the sodium,
Yeah.
it had 11 protons and 10 electrons, but whatever that bottom number is, that's supposed to be like the number of protons and electrons combined, right?
Protons and neutrons combined.
Oh, okay.
So we talked about atomic mass, but we don't ever really think about neutrons when we're talking about like bonds or anything like that. It's usually electrons that we're thinking about first, and then like protons.
Okay, so that has nothing. So that number has nothing to do with the number of electrons that it has. Just protons
Yeah,
and
that's right.
neutrons.
That's right. That's
Okay.
Electrons have to do with the charge, the neutrons have to do with the mass.
Okay,
Yeah, that's a.
that makes sense.
Okay, now we'll break. Okay, so let's get back into it. This is where it'll start to look a little bit more like biology. So we're moving away from this understanding of, can I have everyone's attention? So we're moving away from just trying to understand the basics of chemicals and molecules and what they are and how they interact with each other in general, to focusing more on the chemicals that are actually important for life. So we're going to be understanding the major types of chemicals important for life. We'll sort of look at some short lists that are giving us some general categories of chemicals that we'll encounter in the future. We're going to define metabolism, which maybe has a slightly different definition than what you're thinking of, but it's a very chemistry term. And specifically, we're going to break down metabolism into 2 categories, anabolism and catabolism. We're going to get acquainted with 4 classes of organic molecules. So we said organic molecules are those big molecules that are being made with a lot of carbon. There are actually 4 different types of organic molecules that we're going to want to think about a lot, 4 different classes. And each one of these classes is going to have some smaller versions of those molecules called monomers and some larger versions called polymers. So we'll talk about those terms as well. We're going to name some important salts and electrolytes found in the body. So these are actually our ions. You might just want to add that to your notes. When we're talking about salts and when we're talking about electrons, we're really talking about the ions that we just talked about with those positive and negative charges. That's where those will come into play. And then finally, a final chemistry concept that's going to come into play a lot with biology is the idea of pH. So we're going to define pH and understand the pH scale. This is the idea of acids and bases. And we're going to understand the purpose of buffers in the body that are trying to control the pH in the body. So this is a list of the elements that are most common in the body. We're seeing that it's mostly, at the top of our list, we have oxygen, we have carbon, we have hydrogen, then we start to have some nitrogen. Let's focus on these top three: oxygen, carbon, and hydrogen. Why do you think these are so common in the body? I want everyone to take 30 seconds and think about this. Why do you think these are the top three elements? What sort of molecules we might see that are made from oxygen and carbon and hydrogen? Think about it for 30 seconds, maybe jot down an answer in your notes, and then we'll talk about it in class. Okay, so what are our guesses? Why do we think we're seeing so much oxygen, carbon, and hydrogen? Can someone raise their hand with an answer? Yeah?
As we inhale oxygen, we exhale CO2, and a large portion of our body's water, which is H2O. All three of them use oxygen.
Okay, so there's a couple things there. There was carbon dioxide and oxygen, which are these gases that our bodies are always exchanging for one another. And then I think I heard you say H2O as well, water, right? This is going to be huge. So our bodies are, I want to say it's like 78% water. Like water is everywhere. It's inside our cells, it's outside our cells, it's in all our organs and tissues. It's what makes our blood fluid, right, is water. So a huge amount of water in our bodies, and that's why we're seeing so much oxygen and hydrogen. These percentages I think are by weight, so if you're wondering why like hydrogen is actually is only like 10% and oxygen is like 65%, the chemical formula here is H2O, it's because this is by weight and not by like number of atoms. But that's why we're seeing so much oxygen and hydrogen. That's part of the reason why.
It's what most commonly found throughout our planet/galaxy, so we're only products of our environment and evolution.
What's the it's in that sentence?
Hmm.
Just like all of these elements in general?
Yeah, those are like the most common in our planet.
Yeah, that's a good point actually, that like in the universe there tend to be a lot of these elements. Some of those other weirder elements, there are fewer of those elements that are just floating around, so it kind of makes sense that life ended up built on carbon and oxygen and hydrogen and not silicon, for example, which is something that in some ways has similar chemical properties to carbon. Anything else about why we think these might be found in particularly high numbers, these elements? What about carbon in particular? What have we been talking about with carbon? Carbon had 4 electrons and could form 4 covalent bonds. So what kind of molecules were formed out of carbon?
DNA.
DNA, yeah, among others. So what was one of our general terms for those big molecules that were formed out of carbon? Yeah, the macromolecules or organic macromolecules. Yeah, so we're seeing, water and how important water is kind of explains how much oxygen and hydrogen we're seeing. How important oxygen gas is also partially explains how much oxygen we're seeing, right? So that makes sense. The thing that explains how much carbon we're seeing really has a lot to do with these organic macromolecules. DNA is a type of organic macromolecule. Proteins, sugars, stuff that we're going to see in the upcoming slides. All of these are types of organic macromolecules. All of these are really essential for how the body is functioning and how the body is working. So that's why we're seeing those elements in particular so highly represented in the human body. So let's just list out some of these things. In some ways, it's very similar to what I just drew up there. So water is at the top of our list as chemicals that are important for life. Although, to be honest, we're not going to talk too much about water in the remainder of this lecture. Kind of. When we get to pH, we'll come back to water and why water is, and some of the properties of water. But for the most part, it's just useful to know that water is kind of everywhere. Inside the cells, outside the cells, when we start looking at diagrams of cells. Water is just kind of all around. So that's one of these chemicals that are really important for life. Organic macromolecules. mostly made of carbon, also hydrogen, some nitrogen, and some oxygen as well. Those are really important for life, and we'll see all the many different things that organic molecules do. Let's start to introduce the terms for our 4 types of organic molecules. These are probably going to seem a little bit familiar to some of you, to many of us. Especially if you think about nutrition, you've probably thought about these terms before. So carbohydrates, lipids, proteins, and the last one, nucleic acids, are a little bit weirder. But these are our 4 different types of organic molecules. So we're going to dive into each one of these in a little bit more detail. But when we're talking about organic molecules, these are what we're talking about. Things that we often think about when we think of nutrition, because we're taking in so many of them whenever we're eating plants or animals, formerly living things. We're taking in so many organic molecules and then using it to build our own organic molecules. And then finally, our final important component, chemical component of the body that we've listed up here, are inorganic minerals. So they're inorganic because they don't have a basis in carbon. They're not these, for the most part, not these large molecules at all. These are mostly just these ions that are existing that have really important roles in the nervous system, really important roles in the muscular system, help keep the bones rigid. They have these very specific roles in the body that we'll talk about as we go forward. But just some of the inorganic minerals that we'll think about going forward are sodium and chloride, which we already began to think about, potassium, calcium. So other things we're getting from our diet that are very different chemically than our organic macromolecules. These are little ions that we saw earlier. So now let's return to this word metabolism that I said probably has a different definition than the definition we're used to thinking about, sort of on a day-to-day basis. So metabolism, you might think of it having to do with, you might think of it as having to do with nutrition. It does have to do with nutrition. You might think of it as having to do with energy, or the way the body is like burning fat or using its fuel, and it has to do with all of that too. But really our broad definition of metabolism is just any chemical reaction that's occurring in the body. All of those chemical reactions in the body together, that's what metabolism is. So there's 2 different types of metabolism that we can talk about, 2 different types of chemical reactions that can occur in the body. One is metabolism. This is a breaking down of macromolecules, and this is going to release energy. So when the body needs energy to do something, it needs energy to contract its muscles. It's going to get that energy from metabolism, from breaking down larger macromolecules in a way that releases energy. This diagram isn't really showing us anything in particular, it's just showing us this idea of a larger molecule breaking down. And then we have anabolism, which is the flip side of that. Anabolism is the building up of a macromolecule, and that's going to require energy. So that's what we're seeing here. We see energy going in, and we see all these smaller pieces of some molecule here being built up to form a larger macromolecule here. So that's anabolism. The energy that's released from catabolism, one thing that energy can be used for, I said, is contracting muscles. So that's one reason the body might want to focus on catabolism and release a bunch of energy. But the energy from catabolism, it can also be what is used to fuel this anabolism on this side of this diagram. So because these smaller pieces require some energy to be built up into this larger thing, and because that energy has to come from somewhere, sometimes we say that catabolism is coupled with anabolism, and that just means that the energy that's released from the catabolism of one thing is being used to fuel the buildup, the anabolism of something else. So this energy released from catabolism can be used to fuel anabolism, this is coupling, or it can be used to do other kinds of work, like contracting a muscle, or it might just be released as heat. So the body in some ways does this by accident. All chemical reactions like this, all catabolic reactions are releasing a little bit of heat, and so a normal part of metabolism is the body releasing a little bit of heat. And if the body needs to warm itself up even further, maybe it goes through a little bit more catabolism to release a little bit more heat to sustain itself. So there's a few different kinds of reasons that the body might want to use the energy from catabolism, and a few different ways that energy can be used. But one of them is to build up some sort of macromolecule through anabolism. So these are words that you're expected to know. And so it's useful to have some mnemonics for them. So Where I start with this mnemonic, this one makes a lot of sense to me. So up here you see a picture of a cat. So we're talking about catabolism. So there's a cat in the image. And what is it doing? It's breaking a vase. So if catabolism breaks down macromolecules, and I sort of think about that or remember that, is to just think about a cat breaking a vase. And if you have cats at home, you probably know that they are always trying to push things over and break things. So if you have cats, or at least if they're anything like my cats, that's a very useful mnemonic for you. The other thing to maybe add to this mnemonic a little bit, add to this like memory tool that we're using to remember this, is the idea that when this cat breaks this vase, it's going to shatter everywhere, and it's probably going to make like a large sound. So you can think of that sound as sort of a release of energy. And that's our final component of catabolism that we want to remember. So think about this cat breaking a vase, like breaking down a macromolecule, and that shattering of the vase being a release of energy. And you can remember what catabolism is doing, what the specific sort of metabolism, rather, is doing, breaking down macromolecules, releasing energy. And for the flip side of that, anabolism, I like to think about this clip art person here, who I've decided to name Anna. And Anna has her little construction worker hat, so she's someone who builds things. Anna builds something up, so just the way anabolism builds up macromolecules, and building things requires energy. It's not like breaking a vase where it just shatters. Building things requires Anna to come into work focused and with a full stomach and ready to put in some of her energy into the task that she's doing. So anabolism is building up macromolecules, and it's requiring energy. Energy is necessary for this buildup. So that's a mnemonic you can use. It's a mnemonic I like. Obviously, you can use whatever mnemonics you want. But using mnemonics like that will help you with words like this that might otherwise seem a little bit boring, right? Anabolism and catabolism are probably not words that you're using every day. So you want to use little memory tricks like that as a starting point. So diving into more detail with our organic molecules. We've already kind of covered this stuff, what they're made of, the 4 different categories, the fact that they're these very big molecules, these macromolecules. And we covered this as well, the fact that all living or formerly living things are mostly made of organic molecules. It has nothing to do with whether they're organically farmed. So whether or not these things were organically farmed, they are full of organic molecules. Let's dive into these 4 types individually: carbohydrates, lipids, proteins, nucleic acids. And let's understand the unique roles that they're having in the body. So first, let's just take, actually before we do that, let's understand one interesting thing about organic molecules and the way chemists are describing organic molecules. We talked about our structures, our chemical structures earlier, where you had each of the atoms that are going into this molecule listed here, each of the covalent bonds represented with a straight line. So we talked about these structures earlier, and here's an example of a complicated structure of an organic molecule. Sometimes chemists and biologists get kind of lazy when we're describing organic molecules. And the fact that organic molecules have so much carbon in them, it seems a little silly to write out all those carbons over and over and over again. So chemists sometimes draw these chemical structures in an organic molecule, and they just drop all the carbons entirely. So the way this sort of structure works is that you assume that every point between these lines, here, 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 each one of these points is just assumed to be a carbon. Each one of the lines still represents a covalent bond, like normal. And then anytime you have a carbon, and you don't see it bonded to 4 things, you just assume that all the other bonds are to hydrogen. So this carbon you can see is bonded to this carbon. You just assume that the other things that it's bonded to are hydrogen. So that's how organic chemical structures work. Again, not something you'll be asked to do in this class, maybe in a different class you'll be asked to translate these 2 things. But useful for us to understand because we will occasionally see organic structures like this, and it's useful to understand what that is. Like, oh, this is a big molecule that's made of mostly carbon and hydrogen. we can start to see some of these weirder shapes that I was kind of talking about earlier, these like ring shapes in these chemical structures. We didn't really see that in the chemical structures I showed you before. You do have these chemical rings that form sometimes. You can see that on these organic structures. Okay, so now we get to go into our 4 types of organic molecules. Carbohydrates, lipids, proteins, nucleic acids, and we get to understand the role of each of these specific things in the body. So for all of these classes, we're going to have some molecules in each category that are considered monomers. These are smaller molecules. And sometimes those smaller molecules, those monomers, will be linked together into larger, longer molecules called polymers. So here, we're not really seeing the internal chemical structures of either of these things. This diagram is just calling them monomer 1 and monomer 2. But it's showing you how these 2 different monomers, these 2 separate smaller molecules, can be linked together to form a polymer, or in this case, what it's calling a dimer. This is another case where prefixes are going to be useful. So, mono. Has anyone seen the prefix mono somewhere? Like, what's an example? Yeah. So mono is always going to mean one. Does anyone have a good example of a word that starts with mono where you're using this prefix?
Monotone.
Monotone, yeah. Means like one tone, no variation in tone, just flat, staying in one place. There's another example of
Monopoly?
Yeah. Oh yeah, no, monopoly. If like one company has complete control of an industry. What were you thinking? You talking? That was not one of those things at all. Any others?
Monohydrate.
Monohydrate, yeah. I feel like I've just been lecturing you all about chemistry for a while, but I can't remember what a monohydrate is. Do you know anything about why a monohydrate is called a monohydrate?
I just know creatine monohydrate supplement, that's all.
What?
I just know the creatine monohydrate supplement.
Oh, gotcha. So I'm guessing it's like maybe one hydrogen group or maybe one like water group involved in your creatine monohydrate. I don't know. I could look it up. But yeah, same prefix. So we see those prefixes over and over again. Monochromatic, so would that be like a sepia would be considered monochromatic?
I mean, I thought of it like an art sense where you
Yeah.
stick to one color scheme.
Yeah,
The
yeah.
whole thing.
So all of these things are places where we're seeing this prefix mono and it's referring to one. So whenever we see our monomers, that's sort of one unit that can be built up into something bigger. So then we have the flip side of that, which is our polymers. And our prefix poly means many, so that's the flip side here. Does anyone have any good words that begin with poly? Polydactyl, yeah. Great. So that's like too many toes. If someone has like 6 toes, they're polydactyl. So poly is many. Any others?
Polygon.
Polygon, yeah, many sides. Yeah.
Polyamorous.
Polyamorous. So many romantic partners, which we can sort of contrast with monogamy. So we see these same prefixes over and over again in our lives. Mono meaning one, poly meaning many. Here we're just applying it to organic chemistry. We can, and the specific way we're applying it to organic chemistry is this idea of you can have individual monomers. They're going to be strung together into these polymers. And that brings us to why we're calling this a dimer. So why are we calling, we said this is a polymer, but more specifically it's a dimer. So what does our prefix di here mean? Yeah, I heard it. So di means 2, and that means we have 2 of these monomers being strung together chemically to form this dimer from these 2 monomers. And that's just a specific type of polymer here. Any questions about this stuff? I think sometimes the thing that gets glossed over is like these are two separate molecules, and when they come together and when they're strung together, it's just a covalent bond that's connecting them. So they just go from being these smaller molecules to this larger molecule that's connected together. Question or
And this is
comment?
all organic, right?
Yep, this is all with our organic molecules. So we're actually going to see examples of monomers and examples of polymers for each of those four classes that we talked about, for the carbohydrates, the proteins, the lipids, and the nucleic acids. Each of those categories is going to have monomers, and then within each of those categories, there are going to be examples where those monomers of that category are going to be strung together into the polymers of that category. Okay, so this example that we're looking at here, let's reflect on it a little bit. We have two monomers coming together to form a dimer, a small polymer. Is this anabolism or catabolism? And then taking the answer to this question in mind, do you think it absorbs energy or releases energy? Everyone take a minute and write that into their notes.
Can you say that one more time? I really understand.
Sorry, just answer this question in your notes. Like you should be able to look at this chemical reaction
And say
and
it.
at least make a guess about whether it's anabolism or catabolism.
Okay.
And then you should be able to use that to decide whether it's absorbing energy or releasing energy.
Okay.
Okay, so what are we thinking? Anabolism or catabolism? Who has an answer? Hopefully someone.
Anabolism.
Yeah, so anabolism. And why do you think it's anabolism?
Because you're building.
Yeah,
Adding it together.
Yeah, we're taking two smaller pieces and we're building a larger macromolecule from those smaller pieces. So it's anabolism. And then, is it going to absorb energy or is it going to release energy? Yeah.
Absorb.
Yeah, it's going to absorb energy. Which is just another way of saying it's requiring some energy from some other source to actually occur, to actually happen. So this is anabolism because it's building up a macromolecule, and that means it's absorbing energy because anabolism is always absorbing or requiring energy. And we can have the flip side, so all of our polymers that we can break up, that we can build up in any of these categories of organic molecule can be broken back down again into monomers. So our dimer can break back down into those two original monomers in what's called a hydrolysis reaction. So what about this? Is this going to be anabolism or is it going to be catabolism? You can just say it.
Catabolism.
Catabolism, right? It's the opposite process, it's breaking down. And then does that mean it's going to absorb energy or release energy? Yep, it'll release energy because that catabolism, that breaking down, is always releasing energy. Think about the sound that a breaking base makes as maybe a release of energy. So another useful bit of context, I think, before we do actually get into what any of these categories individually, although we'll get there, I promise, we'll talk about carbohydrates as a specific thing. But just with all of these categories, or at least with carbohydrates, proteins, and nucleic acids, our body is taking these things in all the time. It's taking some of them in as polymers, others as monomers. But for the sake of this example, let's consider the case where it's taking these things in as polymers. The carbohydrates we're getting from our diet, the proteins we're getting from our diet, are initially, many of them, coming in as these polymers. There's a process that occurs in the body, the process of digestion, is actually a lot about breaking down these polymers into these monomers so they can be absorbed into the body and travel through the bloodstream. And then the body is going to want to do something with all those monomers it just took in, all these nutrients. So it's either going to take these monomers and it's going to use them to build new polymers. That's one option. We'll talk about why the body might want to do that in specific cases. But it can do that for energy storage, and it can also do it because it needs the polymers to perform some sort of function in the cell or in the body. So that's one thing the body can do with these monomers that it's created from these polymers. And the other thing it can do with it is it can just send it into the mitochondria of the cell. We'll get there too when we talk about the cell and the cell biology portion of this course. But the one thing it can do is it can take those monomers, it can further break them down and use the energy that's kind of locked up in these monomers to fuel the cell's needs, to fuel the cell's energy needs. So this is kind of useful as we think in particular about carbohydrates and lipids, which are all about the body needing energy and storing energy. It's useful to sort of have this in the back of our mind, what in general is happening to the polymers and the monomers that the body is taking in and that are floating around the body, floating around the bloodstream. Was there a question about something? Thought I saw a hand. No? So finally we get to carbohydrates. We have 3 minutes left, but let's start getting into carbohydrates. This one of our 4 categories of organic molecules. And we can divide carbohydrates. We can say there are examples of carbohydrate monomers, and there are examples of carbohydrate polymers. So when we talk about carbohydrate monomers, the most important thing that we're going to think about is glucose. You might know, especially if you have reason to think about diabetes a lot, that glucose is all over our bloodstream. And glucose is really important for the body because cells are using glucose as fuel all of the time. So glucose is this really important carbohydrate monomer that can also cause problems when it gets out of balance, when it gets out of homeostasis. The glucose is an essential part of how our bodies are working, this carbohydrate monomer that's floating through our bloodstream all the time. Carbohydrate polymers are going to be larger molecules that are built from carbohydrate monomers, so often built from glucose, and there's a few other carbohydrate monomers that can go into building a carbohydrate polymer as well. We have disaccharides, so what did our prefix di mean? 2. So these are going to be carbohydrate polymers that are built of 2 monomers, or monosaccharides. Examples of this include sucrose and lactose and maltose. So sucrose in particular is table sugar, so when you think about sugars, you're often thinking about disaccharides. And then we have larger carbohydrate polymers made of more than 2 sugars. These are starches that we get in our diet, glycogen that we'll see stored in our bodies, and cellulose is actually a particular type of carbohydrate polymer that's coming in from plants. Our bodies aren't actually using or digesting cellulose, but we'll talk about why it's important in a second. So we talked about monomers and polymers. We have that bit of terminology on this slide. The other bit of terminology I just want to point out is the suffix that we're using, saccharides. So saccharides, if you think about something being saccharine, it's usually like you might apply it like emotionally to a situation that's just sort of like sticky sweet. You might say it's like saccharine, like, oh, that song is so saccharine. It's like a really like almost too sweet song. I don't know if that's a good example. But that's where that term is coming from. That term saccharin is coming from the same root as this saccharide, meaning sugar. So a monosaccharide is a carbohydrate monomer or sugar monomer. This disaccharide is a carbohydrate dimer or a sugar dimer. So using these same prefixes and suffixes, we can break apart these different words, referring to monomers and polymers in general, and carbohydrate monomers and polymers specifically. So this is where we'll pick up next time. Like I said, no immediate assignments on the horizon, just look at the study guide, review the notes, keep building your own study documents.